We're going to start off today dealing with a couple of slides. This is an exact slide that you should have seen in the video last night. And it is telling us, okay, once again, this is telling us nothing new. You should know all of this right here, that a balanced chemical equation will tell us what kind of elements are involved. You're going to see on the first example that we do today, which is similar to the second or to the example that you had yesterday. It's going to be aluminum, oxygen. So we are forming aluminum oxide. So it tells you the elements involved, and it tells you the exact number of atoms of each element. A balanced chemical equation will tell us moles. A balanced chemical equation will tell us mass, if we can get the molar mass from our periodic table. It will tell us the number of particles because we know that 1 mole has Avogadro's number of particles, whether it's an atom, whether it's a molecule, whether it's a formula unit. Okay, so we can get the number of particles. We can get the volume of a gas at STP, because we know that if we're at standard temperature and pressure, that any gas has a volume of 22.4 liters. Okay? That is all, right here, from moles all the way down to volume. That is just flux capacitor stuff that we were reviewing yesterday. Okay? So, moles, mass, particles, volume, that's all flux capacitor stuff. Hopefully you got some good review on that yesterday. Reacquainted, so to speak, ourselves with that flux capacitor. And finally, the density. Okay? If we can get the molar mass, and we have a gas at STP, we can get the molar volume, then we can get mass over volume being the molar density. So, a balanced chemical equation, whether you've thought of it this way or not, will tell us all of these things. These are, how many are they? 7 things we can read from a balanced chemical equation. Now, with these balanced chemical equations, we are going to use them to do some conversions. What are we going to convert? Well, today we're going to start off nice and easy and do what we call molar conversions. We're going to go from moles to moles. We're going to go from mass to moles, moles to mass. Mass to mass, mass to volume, volume to mass, volume to moles. Now you might say, Mr. Braun, we have already done that. That is flux capacitor stuff. That is a correct statement. You have already done that. Now, what we are going to do is we're going to take it a step beyond. So we're going to have a balanced chemical equation, and we're going to convert from one substance to another. Okay? We've been doing it by staying with the same thing. For instance, I can take moles of sodium chloride to get to a mass of sodium chloride. I can go moles to mass of sodium chloride. Well, now we're going to switch it up. And you're going to see how I was preaching and preaching and preaching. I would set up conversion boxes. I would do it exactly like this. Okay? I've been doing this, folks, for 20-some years. Okay? This is the best way that I've found to do it. All right? The best way that I've found to do it. So we're just going to jump right on in with this, and let's go here. go ahead and copy this example down, and then we will work the example. Aluminum reacts with oxygen to form aluminum oxide. Find the number of moles of aluminum reacted if 1.57 moles of oxygen are reacted. So, when I am doing this problem here, I am asked to find the number of moles of aluminum. I'm given the number of moles of oxygen. So, what I need to do is first come up with a balanced chemical equation. So, I have to go back, and it's easy here because they tell me, the problem tells me everything that I have. I just have to use my knowledge of writing formulas. So, I know that aluminum will react with oxygen. Okay? Aluminum will react with oxygen. Why did I put O2? Because oxygen's a super 7. It's a diatomic. Okay? Aluminum will react with oxygen to form aluminum oxide. Now, I can tell that I have a skeleton equation here. It is not balanced. So once again, now I've got to go into my balancing. We've done that before. We need to balance this guy. I see my biggest problem being my oxygens right now. So I've got 2 here, I've got 3 there. 3 and 2 make 6. So I'm going to take each one of those to 6. So I've got my oxygens balanced on both sides. I put a 4 here. I now have a balanced chemical equation. Okay? Once again, nothing new. But can you see, if you would have missed the super 7, can you see how that would throw your entire answer off? Okay, so we have to be perfect doing this stuff, or it's going to throw us off. So, what I'm going to do now is I'm going to use this balanced chemical equation to convert from moles of oxygen to moles of aluminum. I know that I'm given 1.57 mole of oxygen, correct? I'm going to set up a conversion box, just like we have been doing, but I'm going to use what we call the molar ratio. The molar ratio. Well, what is the molar ratio of aluminum to oxygen? 4 to 3, right? 4 moles of aluminum, 3 moles of oxygen. I just have to figure out what I want to put where in my conversion box. Now, what do I want to cancel out? Moles of oxygen. So I'm going to put that where? Numerator or denominator? Top or bottom? Bottom. So I'm going to put 3 mole of oxygen. Where did I get that 3 at? From my balanced chemical equation. Right there is where the 3 came from. What am I trying to convert this to? Well, not trying to. What am I converting this to? Moles of aluminum. So how many moles of aluminum I got to write there? 4. 4 moles of aluminum. I close out my box now. I go back and check to make sure that my moles of oxygen cancel. It does. So what is my answer going to be? Labeled. Moles of aluminum is going to be the label on my answer. So all I have to do now is my math. I take the 1.57. I multiply that by 4. And then I take that value and divide it by 3. How many sig figs? I go back to my original problem. How many sig figs do I have there? 3. So I'm going to have 3 sig figs in my answer. So my answer is going to give me 2.09 mole of aluminum. So this is telling me if I have 1.57 moles of oxygen to react that completely, I need to have 2.09 moles of aluminum to react completely with the 1.57 moles of oxygen. Now, could I take it a step further and say how much aluminum oxide, how many moles of aluminum oxide I should get? I could do that. That would be a different molar conversion using a different molar ratio. But nonetheless, I could get that done. Here is our second example. Go ahead and copy down the example, then we'll work the problem. The problem tells me that aluminum reacts with iron 3 oxide. Find the number of moles of aluminum reacted if 2.43 moles of iron 3 oxide are reacted. Now, this is starting to get to some of the beauty of these questions, because right now, as I'm looking at this, I can see that I have the 2 reactants. Do I have any of the products? I do not. So I've got to determine, first of all, what kind of a reaction is going to happen here. Okay? This is, like Kane said, this is a single replacement reaction. So I'm going to write out my reactants. Aluminum will react with iron 3 oxide. Now, I need to determine whether this reaction will occur. So what do I need to do? I need to check my activity series. Will aluminum replace iron on my activity series? Is aluminum more active than iron? I would bet if I were guessing, I would say yes, because Mr. Braun's not going to put an example on here that doesn't happen. Okay? But look at your activity series. Anybody got it out? Is aluminum going to replace iron? Absolutely. Aluminum's higher. So, what am I going to have formed? I'm going to have formed a new salt and a new metal. So my new salt is going to be aluminum oxide, and my new metal is going to be iron. Now I need to balance my chemical equation. And as I'm looking, my oxygens are balanced. If I put a 2 here and I put a 2 here, I have both my aluminum and my irons balanced also. Would you agree? Now, look at what we've just done, folks. In order to be even able to do the problem, I had to determine what my reactants were. I had to determine that it was a single replacement reaction. I had to determine whether on my activity series that aluminum would replace iron. So there's a whole lot into the game, and I haven't even begun to do my math yet, have I? So I have now got my equation where I need it to be. I'm going to go through and do my conversion. So, says find the number of moles of aluminum. So I'm finding the moles of aluminum. And what am I given? I'm given that I have 2.43 mole of iron 3 oxide. I do my conversion box once again, and I can see that number of moles of aluminum. I can see that 1 mole of Fe2O3, there's where I got my 1, will give me 2 mole of aluminum. I go back to my problem, and I say, okay, moles of iron 3 oxide cancel out. My new label is going to be moles of aluminum. That's what I'm trying to find. So I go through, and what I'm doing is I'm taking 2.43, and I'm multiplying that number by 2, and I'm coming up with a value of 3 sig figs, 4.86 mole of aluminum. Now, was that math very hard? Taking the 2.43, timesing it by 2? No, the math is easy in this particular question, but getting to the point to do that math is the tough part. All right, getting to that point is the tough part. Now, I've got one final one that we're going to do. So go ahead and copy down this example, and then we will work the example. Potassium phosphate reacts with magnesium chloride. The number of moles of magnesium chloride reacted, find the number of moles of magnesium chloride reacted if 5.0 moles of potassium phosphate is reacted. Once again, in this problem, I have potassium phosphate. It reacts with magnesium chloride. What type of a reaction is this going to be? A what? A double replacement reaction. Specifically, if you're looking at your helper sheet on your double replacements, this is going to be 2 aqueous salts, right? So, I need to flop my cations. So, I'm going to get potassium chloride, and I'm going to get magnesium phosphate. Now, the first thing that I'm going to check is I know that I need to have one of these soluble, one of these insoluble. So I am going to check my potassium chloride, soluble, my magnesium phosphate is insoluble. So this one is a solid. This one is aqueous. Will this reaction occur? Absolutely. Now what do I need to do? I need to balance my equation. And this guy's going to be a little tough to balance, but I look and I say, okay, I'm going to start with my phosphate. So I'm going to put a 2 there because I can see over here I have PO42. So if I put a 2 there, that is going to give me 6 potassiums. If I put a 6 there, 6 potassium here, 6 potassium here. That means my chlorines are 6 also. So if I put a 3 there, I balance my equation, don't I? Let me go back and double check. 6 potassiums, 6 potassiums, 2 phosphate, 2 phosphate, 3 magnesium, 3 magnesium, and 6 chlorine, 6 chlorine. I have a balanced chemical equation. Now I'm ready to work some math. Okay? Find moles of magnesium chloride. So I have 5.0 moles of potassium phosphate. I put my conversion box. I'm trying to find moles of magnesium chloride. Well, I know that 3 moles of magnesium chloride has a molar ratio with potassium phosphate of 2. It's a funky looking M. Once again, just before we go any further, is everybody okay with this molar ratio step right here? And where I get it? Comes directly from where? The balanced chemical equation. So I come up here and I say, okay, moles cancel. My label is going to be moles of magnesium chloride. Okay. I look at this and I say, okay, what is 5 times 3 is 15 divided by 2 is going to give me what? 7.5? How many sig figs or 2 sig figs okay? Yeah. So now I have determined that if I have 5 moles of potassium phosphate, to react that completely, I'm going to need 7.5 moles of magnesium chloride.